Let's start, folks. I want to wrap up the discussion on memoryless systems from last time. We looked at systems in terms of their throughout this course we look at systems in terms of their inputs and outputs. The input of the system I've broken down into a set of functions from some domain to some range, and the output signals from some domain to some range. Typical D would be the set of reals or the set of integers. And A and B typically would be reals or complex. But A and B need not be the same in this discussion. They don't even have to be real or complex. They can be any sets. Need not be the same. And we define memoryless systems as systems where when you look at y as a function of time, where tau is in D, if you can find a function f such that f as a function of the input at that exact instance produces the value of the output at that instance. So if an f exists, where would the domain and range of f have to be? Domain is the range of x, which is A. And the range of f would have to be B. So if you can find the function from A to B such that when you plug in the instantaneous value of the signal x, you get the instantaneous value of the signal y. And this is true for all tau in D. So if there exists such a function for all tau, then the system is called memoryless. Then f is memoryless. Plainly speaking, the output at any given point in time uses no value of the input at other values in time. And we discussed some of the consequences of this. For example, let's call them corollaries or implications. So if you're looking at the same signal at two different instants in time, if x at tau 1 is equal to x at tau 2 for two different points in time, what can you tell me about the outputs at tau 1 and tau 2? They should be equal. Okay? Because the function small f cannot distinguish between these two time instants, because at these two time instants, the value of the signal is the same. So this would be a situation like this. This is tau. This is tau 1. This is tau 2. And this would be x at tau 1. And this would be x at tau 2. If the system only cares about the instantaneous values of the input signal, then it can't distinguish between these two time instants because the input signal acquires the same value at these two time instants. Another consequence is that if two input signals, x1 at tau 0 is equal to x2 at tau 0. So you have two different input signals. But at a particular value of tau, namely tau naught, they happen to be equal. This would be a situation where you have one function and another function. So this would be x2. And this would be x1. And at tau 0, they're equal. Okay, what can you tell me about the corresponding outputs? They must be y1 at tau 0 must be equal to y2 at tau 0. So you can play around with all such permutations of these scenarios and use these corollaries if you ever want to disprove that a system is memoryless. Find two instances in time, for example, where the input signal has the same values and see if the corresponding output values are the same. If they're not, then you can write it off as a system that has memory. So let's go back to actually, we had some properties that we discussed last time and the time before that, namely causality and time invariance. And a couple of you picked up on the relationship between memoryless systems and causal systems, and the relationship between memoryless systems and time invariant systems. So what was that relationship? How do you relate causal systems and memoryless systems? The rest of you. Memoryless implies causality. So every memoryless system is causal. So memorylessness implies causality. The converse is not true. Now, this is true because, well, if the system only depends on the value of the input at the current instant in time, then obviously it's not looking into the future. So it's not, to produce y at tau, it's not waiting for some future value of x. So that much is straightforward. The converse is not true. Not every causal system is memoryless. And there are plenty of examples, and when we do some of the examples, you'll see. In fact, let's do one. So one of the things we described with regard to causal systems is when you have suppose I have this system. Y at time n depends on the value of y at n minus 1 plus x of n. LTI system. What was the impulse response of this system? You remember? I mean, you'll see this example so many times, you've got to etch it into your minds. H of n is alpha to the n, u of n. Okay? So when you write out the output in terms of the input in a non-recursive way, using the convolution expression, what would you get? Summation m of h of m x of n minus m. Correct? That's the convolution expression. Now plug this into that expression and tell me what you get. What are the limits of m? And what is inside the summation? What's with all the silence? You don't like talking to each other or what? Have there been political fights? Do your thing, Mitbo. You want to take it on yourself? What is the output in terms of the input? I want you to plug in the expression we have for the impulse response into the convolution expression and write y only in terms of x. That difference equation relates the output y with it's a recursive form or description of the system. I want you to write an expression that's only between y on one side and x on the other side. Is the question clear, or is there some ambiguity still? Okay. So who wants to take a shot at it? You are? Mohsen. Summation goes from where to where? So because of the unit step, it goes from 0 to infinity. Alpha to the m, x of n minus m. And can you give me a few terms in this? Start with m equals 0. X of n plus alpha x of n minus 1 plus alpha squared x of n minus 2, and so on. Okay, so if you were to write the input-output description of the system in a non-recursive way, this would be it. Is this system causal? Does the output at time n, at sample n, depend on any future values of the input? No. So this system is causal. This system is causal. Because y of n has no dependence on x of n plus 1, x of n plus 2, and so on. Okay, so this system is causal. Is it memoryless? Why not? Yeah, because it's got to store all these values if you want to implement it this way. By the way, this brings out a point about the implementation of this system. How do you implement this system? You can't implement it using this equation because this goes all the way to infinity. So the only way you can implement it on a computer is using the recursive form, where you need only one delay element. But this brings out the point that the values of the input at other times play a role in the output. You can also see it if you write down a few recursions of the difference equation. But the dependence in y of n on x of n minus 1 is implicit in the previous output value. And that's why I wrote it in explicit form here. A simpler example would be this. So let's make that comment. The system is not. This system is not memoryless because, for example, y at n depends on x at n minus 1. So this is an example of a system that is causal but not memoryless. And that's why I have that red backward arrow with a cross sign on it. So although every memoryless system is causal, not every causal system is memoryless. Here's another example. Y of n is x of n plus x of n minus 1 divided by 2, a 2-point averager. We've dealt with this in the past. We've figured out its frequency response and analyzed it to death. What's the impulse response of this system? Two spikes. Where and where? 0 and 1, and height 1/2. So this is the impulse response of this system. Is it causal? It's causal because y at n depends only on the current and previous values of x. So this is causal. But again, it's not memoryless, because of the presence of this delayed version of x in here. By way of review, by the way, you should keep in mind that LTI systems are causal if and only if their impulse responses are 0 for negative values of the time samples. Yeah. And that's the case in both of these situations. Okay, so that's the relationship between memoryless systems and causal systems. What about memorylessness and time invariance? And this is where we diverge from the common literature on memoryless systems. So if you pick up a typical textbook on signals and systems, they will differ with us on this issue. For our definition of memorylessness, every memoryless system must be time invariant. So memorylessness implies time invariance. And that's simply because of the relationship between the input and the output. So if I have y of tau, and I know my system is memoryless, I know that there's a function f such that it's a function of x at tau. Now, define x hat to be a shifted version of x. What's y hat? F of x, f at, evaluated at, x hat of tau. The system doesn't care what you call the input. You can call it x hat, x tilde, whatever. The system just takes whatever value you give it at that instance of the input and spits out a value for the output. But now you can replace this with, you can replace the argument with x. And that's x of tau minus t naught. And the answer to the following question determines whether the system is time invariant. Is this equal to the original output shifted by the same amount? If the answer is yes, then the system is time invariant. If the answer is no, even for at least for one value of tau or for one value of the shift, then the system cannot be time invariant. So what's the answer in this case? What is y of tau minus t naught? F of x tau minus t naught. Wherever you see tau on the right-hand side, you replace it with tau minus t naught. And so you notice that these two are equal. So the answer is yes. And therefore, every memoryless system must be time invariant. So this is the example I'm about to put on the board is one where you'll see appear almost in every signals and systems book you pick up. And that's modulation. X of t gets multiplied by some other function, g of t. And your output is x times g. Okay? This is, well, this is a first. I've never had makeup on the board. This is our system. And you can think of this as, for example, being a cosine at some frequency. It doesn't have to be a cosine, but that's something we've seen before and are comfortable with. So any book on signals and systems that you look at will call this a memoryless system because this system depends on x at t and at no other value of x for other times. The problem is that you cannot implement this system without having memory elements inside. So for example, if this is a cosine, that means this system has an internal oscillator. And there's no way you can build an oscillator without inductances and capacitances, both of which are memory elements. Yeah? Well, because this is what makes, for exactly the reason I just mentioned, that if, so for most signals and systems books, they call a system memoryless if you can find the function f that is not only dependent on x at time t, but may also be a function of t. Most textbooks. That's what this is. This is a function not only of x of t, but also of t. And the way it depends on t is through this cosine, or that g of t. This is a time-varying system. So other textbooks allow memoryless systems to be time-varying. But our strict definition of memorylessness, which imposes the condition that you cannot have any memory elements inside this box. You just can't. You can't have an oscillator in there. Because an oscillator requires keeping track of time. Notice this system keeps track of time. And if you have to keep track of time, you can't do that without memory. You have to have an idea of, have some stored information about what the time origin is, and then you count. But a memoryless system cannot have that. And that's why we insist on this particular definition. Now, it may be just going up against a notion, a tsunami of established conventional wisdom. But I just want you to keep in mind that this is the difference. So if you pick up other textbooks to do practice problems on, be careful about situations like these. In our case, according to our definition, every memoryless system will be time invariant. Let's do one more example, and then we'll take a break. So again, I have one of those situations where I only partially describe the system for you. And in this case, the input signal at 2 is an impulse. So this is x. And the output signal at 1, 2, 3 is 1, 2, and minus 1. Can this system be memoryless? Just one question. Memoryless. And then time invariant. So that's what I want you to talk to your neighbors about for a couple of minutes and sort it out. Oh, one thing I forgot to tell you. This system is causal. But you don't need that to answer the first question. You don't need causality to answer the first question. Actually, what the heck, I'll ask one more question too. Can it be linear also? Okay. Mohsen, you get to pick the next person. Yellow. Max. Go for it, Max. Not memoryless. Why? How do you know that y at 1 depends on x at 2. I haven't told you what the exact mapping is from here to here. I've just told you that when I give you a shifted impulse, that's what you get. Here's one of the tests that we gave you. Can you find two values of the input signal that are equal, but the corresponding output values are not equal? So look at the input signal. Remember, we said this system is memoryless if y of n can be written as, and I'll put a question mark on it, some function of x at n. And we said that if you find two values of the input signal that are equal, then what must be true about the output? They must also equal. So can you find two instants in time? In other words, if this is not true, then this cannot be true. Can you find two instances in time where x n1 and n2, can you find n1 and n2 such that x n1 is equal to x n2? Looking at that signal up there. What's the value other than at the spike? Everything else is 0. So give me two instances in time where the input signal values are equal, but the output signals are not. X of 1 and x of 3. X at 1 is equal to x at 3, but y at 1 is not equal to y at 3. So this system cannot be memoryless. What do they call it? F. F cannot be memoryless. Okay? The system is not time invariant. Why? By 1. Okay. So let's go to this board. So which way do you want to shift it? Shift it to the left by 1. So let x hat be x of n plus 1. So we're shifting it to the left by 1. This is x hat. Okay? Okay. Your output will be shifted to the left by 1. And where does the output start? At 1. So now it starts at 0. 1, 2, minus 1. So this would be y hat. Okay? So x hat is equal to x for all n up to and including what? 0. But y hat at 1 is not equal to y of 1. This means it cannot be causal. Right, so this is a contradiction. Yeah. 0. Y hat at, oh yeah, 0. So these two are equal all the way up to 0, so you can't compare the values at 1. You have to compare the values at 0. Yeah. So this signal x hat all the way up to and including 0 is the same as x all the way up to and including 0, but the values of the outputs are different. Yeah. You can also use that argument. Yeah. Yeah. So remember, the system is, so what was that statement? Causal and time invariant, then the output cannot precede the input. Okay? So if the output does precede the input, which is this case, then it's either not causal or not time invariant. Not causal is false because I've told you the system is causal, so it must be not time invariant. Yeah. What do you mean symmetric? No, because I haven't specified what that small function f is. That depends on that function you find. This function f. That's arbitrary. That's any function from A to B, which I put up on the first board. You don't know what the structure of that function is. Symmetry across what? What do you mean by vertical? No, f is some function. You give it some input value. This is f. If the input at time n happens to be that value, the output at time n happens to be that value. That's it. What you can't have is a situation where you have f like that, because that won't even be a function. Because then for the same value of x, you can't spit out two different values of y. But f can be any function, and this horizontal axis is taken from A. This vertical axis is taken from B. If you look at your earlier notes from an earlier board, I said f must be from A to B, where A is the range of the input signals. So input signal is from some domain to A, and output signal is from some domain, the same domain to some other range B. So f takes a value from here because that's its argument. Its argument comes from A. And its output is B. So its range has to be B. But aside from that, there's no structure. Okay, let's take a break. And then we'll, oh, no, we haven't finished the linearity yet. So what about linearity? Same relation. Linear and causal implies not P. So P implies not linear or not causal. Okay? For this statement to be true, at least one of these two must be true. Not causal is false, because I've told you in the problem the system is causal. So it must be that this must be true. Must be true. And this is exactly the argument down here that you can use. Well, that's how we got this expression. Yeah. Okay, take a break, and then we'll shift gears entirely. A very important juncture in the class. We are about to go into discussions that have the word Fourier in them. And so we're finally getting to the real meat of the class. At the beginning of the semester and during several lectures, I mentioned to you that in this class we hop between the time domain and the frequency domain. And you've seen many examples of that. But starting today, we actually start decomposing signals in terms of a linear combination of complex exponentials. That's what the critical core of everything that I'm going to talk about for the next several weeks will be. You already know that you can decompose signals. Already know that if you have a signal, and I'll start with discrete time because that's the easiest format and context to describe this. If you have a signal x of n, let's say this is minus 1, 0, 1, 2, and these are whatever values they are. You already know how to decompose this into a linear combination of impulses. Right? You can write this as an impulse at minus 1 scaled by, let's put numbers on them so we, let's say 1, 2, minus 3 halves, and let's say this is 3 halves. Okay? Let's make it 5/4 just so that they're all different. 5/4. So you know how to split this into a linear combination of a bunch of impulses. 1, 2, 3, 4. 3, 4. Where this one will be at minus 1 times 1. This one will be at 0 times 2. This one will be at 1 times minus 3 halves. And this one will be at 2 times 5/4. Okay? So you already know how to decompose a signal into its constituent, into a linear combination of shifted impulses. And we did this using the closed form, minus infinity to infinity, x sub m, delta of n minus m. So it's a linear x, the signal x at any sample is a linear combination of shifted impulses. We've already done that. And the reason we decompose the signal in this way is that we know what kind of a behavior is that we deal with LTI systems. And for LTI systems, all we need is to characterize what the response is to one of these impulses. And from that, we can infer the relationship, the input-output relationship for any arbitrary input. So one way of decomposing signals was using the shifted impulses. So with LTI systems, if I send in delta into the system F, I get F, let's put the n dependence there, F of n. So if I have a linear combination of these impulses, then, so if this is x, then the output is the same linear combination of the corresponding responses. That's how we got the convolution expression. So this is a way of decomposing a signal in the time domain in terms of shifted impulses. But we also saw that complex exponentials play a special role when it comes to LTI systems. When I sent in a complex exponential e to the I omega naught n, what did I get out at the other side? F of omega naught e to the I omega naught n. So now if I can somehow split an arbitrary input signal into a linear combination of complex exponentials, then what am I going to get out at the output? I know what the system gives me when I give it one complex exponential. This is LTI. I'm talking about LTI systems here. This is LTI. I give it a complex exponential. I get the frequency response evaluated at that frequency times the same complex exponential. Now I take a linear combination of these complex exponentials. What am I going to get out at this end? Linear combination, where these are part of the coefficients, xk, and then what? F of omega k e to the I omega k n. So now we have the two parallel tracks. We know pretty much everything we need to know about splitting a signal in terms of a linear combination of lollipops. That's easy. What we are about to start learning is splitting a signal into a linear combination of complex exponentials. And that's the bridge between the time domain and the frequency domain, because these are now frequencies. Right? Now, the linear combination that I'm talking about is not always in the form of this summation of these complex exponentials. When we get to the more advanced topics in the class, this summation will turn into an integral, because the signal that I'm dealing with does not necessarily have a countable set of frequency components in it. It may have a continuum of frequencies inside of it. And that's the topic for a little later. So we'll start with the easiest case. We'll start with the easiest case, and let me just put out the roadmap. This is what we're going to be doing. This is our roadmap. We have discrete time signals, and we have continuous time signals. We further split these signals into periodic signals and aperiodic or non-periodic signals. It turns out that when we discuss this bottom row, our discussion will also include periodic signals, but that will be secondary in importance. So broadly speaking, we have discrete time signals, we have continuous time signals. In each of those categories, we have periodic and we have aperiodic. And our map will be in this way. I'm going to go first here, then to the right, then to the bottom left, and then to the bottom right. Here we discuss the discrete Fourier series. Or the DFS. Here we discuss the continuous time Fourier series, or just simply known as Fourier series. Those of you who have taken a course in physics or maybe some applied math courses, this is probably where they start teaching Fourier series with. So continuous time, periodic. Then from there we move into discrete time. This is where things get meatier. Discrete time Fourier transform. That's the DTFT. And then we have the CTFT, continuous time Fourier transform. So that's our roadmap. We start with the simplest case, which is the set of discrete time signals that are periodic. This is the easiest to analyze and the easiest types of signals to break into a linear combination of complex exponentials. That's what we're going to do for the next 20 minutes and probably the next couple of lectures, and before I move into Fourier series. Okay? Once you're done with this, then you'll know a whole lot of things about filtering and what all this talk about. All of this will make a heck of a lot more sense out of what you've done with. Sorry, I'm a little out of it today. of the frequency response that you've been studying so far. So far we've been talking about frequency response. It gives you a mapping from the time domain to the frequency domain. In each of these categories, we have not only that mapping that goes from the time domain to the frequency domain, but in each of these you'll have a pair of equations, the second one of which is missing from your vernacular so far. And that's the mapping back from the frequency domain to the time domain. And you'll complete that loop. And so you'll be able to hop between the time domain and the frequency domain with ease. And that's what we're going to say in this phase of the course. So let me start with our first category. So we're talking about discrete time, periodic signals. All right. So here's an example of a discrete time periodic signal. 1, 2, 1, 2, 1, 2, and so on. 0, 1, 2, 3, minus 1, minus 2. I'm going to develop the Fourier series expansion for these kinds of signals in two ways. One, using pure algebraic manipulations. And then I'm going to do a geometric analysis of what goes on. The geometry comes from here. If you look at any period, you can take the values of the signal in that period and stack them in the form of a vector. Right? I take one period. I can stack the values of the signal in that one period in the form of a vector. When I split the signal into a linear combination of impulses, that's the same as saying I take this signal, or this vector, and split it across two canonical vectors of this form, where this would correspond to the impulse at the origin, this would correspond to the impulse at 1, and you have your coefficients. You see that? So this would be x at 0, this would be x at 1. This would correspond to delta of n. This would correspond to delta of n minus 1. Now, if you had a periodic signal that had a larger period, you'd have several more of these, and the vectors would be longer. If this had been a periodic signal with period 3, your vectors would have had 3 components. There would have been 3 elements in your linear combination. Okay? And that's exactly what this splitting is. Except now, instead of a single spike here, you have a spike, but with period 2. So you have spike, 0, spike, 0, spike, 0, and so on. So this would be 0, 1, 2, 3, minus 1, minus 2. And then the other one, corresponding to this, would be 0, spike, 0, spike, 0, spike. Minus 2, minus 1, so on. You see that? Periodic impulse train. One is just shifted relative to the other. I only need 2 of these to describe this arbitrary signal of period 2. If this had been a periodic signal with period 3, I would have needed 3 of these. And the period would have been 3. So for a periodic signal of period p, how many of these coefficients am I going to need, and how many of these vectors am I going to need? P. Okay? This is kind of like looking at, in the case of a periodic signal with period 2, it's sort of like looking at a vector in two-dimensional space that you want to describe in terms of these canonical vectors. 1, 0, 0, 1, and you have your vector x. And how do you find the coefficients in that linear combination? What is it that you know from your high school? What's the magic word? To find how much of this I need, what do I need to do? Project. So I project onto this axis along this vector, and this value will be what? Huh? If this x is x0, x1, and let's call this phi 0, and let's call this phi 1, what will this vector here be? x0 times phi 0. And you do something similar up here, and this will be x1 phi 1. Okay? So that's the simple decomposition of a vector into a linear combination of canonical vectors, orthogonal. Notice this red and the blue vectors are orthogonal. And each of them has a 1 in one entry and 0 in the others. Now you can imagine if I'm going into a periodic signal into a space of periodic signals with period p, I'd have to draw something in p dimensions, which makes it messy, and it's impossible. So 2 dimensions is where we can describe this story with ease. Now, what happens if I if I want to decompose the same vector x in terms not of these two canonical vectors, but some other orthogonal set of vectors. So let's say this is phi 0, which is 1, 1, and phi 1, which is minus 1, 1. What do I do then? This is essentially the difference between splitting a signal in terms of impulses and splitting a signal in terms of complex exponentials. That's exactly the difference. The analogy runs almost perfectly with this geometric interpretation. All you're doing is you're changing the orthogonal vectors that describe your entire space. You had a question? Yeah, you project. So to find the component along this vector, you take this vector and you project. And you take this vector and you project. Projection in this Cartesian space means what? How would you project this vector onto? What's the operation you perform? Dot product, right? So you want to write x as a linear combination. I'm going to write that as capital X, x0, phi 0, plus capital X1, phi 1. Okay, I don't know what these coefficients are. In the other case, they happen to be the entries in the vector that defined x. But here, that's not the case. So to find each of these, what did you do? What does it mean to project this onto, let's say, phi 0? Dot product. Let's use the same notation you're used to. X dot product with phi 0 on the right-hand side gives you what? X naught is a number. I don't know what it is. And then what? X, oh, I'm sorry, phi 0 dot phi 0 dot, you got to take the dot product of each side with phi 0. Isn't that what you're telling me to do? Phi 0 dot phi 0 plus, that's a number, phi 1 dot phi 0. And what can you tell me about the second term? It's 0, because they're orthogonal. These two vectors, phi 0 and phi 1, are orthogonal to each other. So when I take the dot product, I get 0. And that's the wisdom of picking these two vectors to be perpendicular to each other. I go here. Let's do a concrete, let's put in concrete numbers here. So let's say this is 3, 5, okay? So my vector x is 3, 5. My phi 0 is 1, 1. My phi 1 is minus 1, 1. When I say x dot with y, it means in 2 dimensions, I take the transpose of the vector x and I multiply it by the vector y. In other words, I take 3, 5, and I multiply it with y1, y2, or y0 and y1. And what do I get? 3y0 plus 5y1. In general, you'll get x0, y0 plus x1, y1. So now here I have x that I want to represent as a linear combination, x which is 3, 5, I want to represent as a linear combination of 1, 1, which is phi 0, and minus 1, 1, which is phi 1. So what happens when you multiply? When you take the dot product? The dot product of x and phi 0, you're claiming, gives you what coefficient? Huh? X naught. So take this dot product. You have 3, 5 times 1, 1. What is that? But on the other side, you have x0, phi 0, so you transpose that, plus x1, phi 1. So this whole thing is now x0, phi 0 transpose plus x1, phi 1 transpose. I've taken everything and transposed it. And I'm multiplying this by what? Huh? 1, 1. What do you get? This times this gives you what? 2x naught, or x naught, phi naught, dot product with phi naught, which happens to be 2, plus x1, phi 1 dot product with phi naught. And this is what? What happens when you take this dot product? 0. Okay? So how do you find x naught? X naught equals what? X naught equals this, x transpose phi naught over phi naught transpose phi naught. And that's equal to 8 over 2, which is 4. So I'm saying I want to express x as a linear combination of two vectors that are orthogonal to each other. In this case, finding that linear combination was very straightforward. You eyeball it. You say, oh, I know how much of this I need. It's just that much. And I know how much of this I need. It's just that much. So you didn't have to go through all this. But implicitly, that's what you're doing. But when I change now the vectors to something different, 1, 1, and minus 1, 1, I still make sure they're perpendicular to each other. They're orthogonal to each other. But now figuring out how much of this you need and how much of this you need to create this yellow vector is not that clear. And so we have to be methodical. And the way we do it is we assume this decomposition in terms of phi 0 and phi 1. And then we say, OK, to figure out this coefficient, I'm going to exploit the fact that these two are perpendicular to each other. So I'm going to take the dot product of the whole thing with one of them. And that's what this is. When I take the dot product of the left side with phi 0, that's what it is, I get this number. When I take the dot product of the right side with phi 0, the dot product of a sum is the sum of the dot products. So I have to take this dot product with phi 0 and this dot product with phi 0. These two are numbers, so they just stick out. So I have the dot product of phi 0 and phi 0, and the dot product of phi 1 and phi 0. Phi 1 and phi 0 are perpendicular, so their dot product is 0. So the only term that's left on the right-hand side is the one that involves the coefficient, the index of the coefficient that I'm interested in. And that's what you see here. So I have a combination, the sum of dot products is the dot product of a sum is the sum of the dot products. The second one is 0. I'm left with only this term. What can you tell me about phi 0 dot product with phi 0 in terms of geometry? It's equal to what? Magnitude of phi 0 squared. It's the length of phi 0 squared. That's what it is. So, but then the coefficient that you're left with, this is if you know what phi 0 is, you know what the square of its length is. That's 2. What is the length of phi 0? Square root of 2. So the square of that is 2. And that's where this 2 comes from. And when you project x onto phi 0, which is to take the dot product, you happen to get this number. This magical relationship is going to show up over and over again in our discussion. So yeah. Well, how are you going to take the dot product of phi 0 and phi 0? The dot product of any two vectors, x and y, is the transpose of the first times the second, or the transpose of the second times the first. That's how you take the dot product. OK, we'll continue this next time.